Hello, my name is Dmitry and welcome to the DPLABS channel. Yeah. Fan. Today our guest is Evgeny. He's from the city of Kursk and is participating in a project to develop an inverter. In addition to the conceptual design, he has already brought a finished prototype and now we're going to demonstrate how it works. So Evgeny, tell us about your Uber device, its features and everything else.
Good afternoon. As part of the competition, a prototype inverter was developed for demonstration purposes. The prototype was mainly built using ready-made components, meaning that pre-made power modules were used, and later I can show you the custom-designed control board. Its main specifications are a maximum voltage of 400 to 450 volts and a maximum current of 400 amperes. A key feature is that you can use virtually any feedback interface from the motor. This includes Hall sensors, resolvers, various encoders, incremental, absolute. So the hardware platform allows you to experiment with anything you want just by updating the software. So essentially, what we have here is an experimental laboratory prototype on which you can test everything. I can show it to you up close. The enclosure was designed in a 3D system and printed on a 3D printer. Inside, you can see the power module itself, and underneath it, there is a film filter capacitor. The module is mounted on an aluminum heatsink, which also serves as a water block. So if cooling is needed, you can run cold water through it and cool it accordingly. The current advanced sensors are primarily based on Hall effect elements, which inherently means they provide contactless measurement with excellent galvanic isolation. On the side of the device, there is a dedicated box containing the essential control boards, various necessary control connectors, crucial feedback connections, a separate and independent power supply, and as is customary, a standard USB interface for conveniently connecting to a computer system. At this very moment in time, we have successfully connected a 3-phase permanent magnet synchronous motor. This is specifically a PMSM motor from Nissan, which is either from a Leaf or a Note vehicle. It has a power output of about 60 kilowatts and a voltage of 300 volts. For the experiment, we connected this entire system to a 3-phase network through a variac, installed a diode bridge, and just in case, there's a contactor circuit breaker to disconnect in case of an emergency. So, basically, now we'll demonstrate how it works. Oh, and for added realism, we also connected a gas pedal. From the vase. From the vase, yes. And it's as if the gear selector is off and there's drive and reverse.
Yeah. I would like to add that naturally we will not be able to test it under load now, since for this we need to load it with nothing. For this we need a stand. We are now in the process of developing a load test stand. When it's ready, I think we'll really put this system through its paces. But at the moment, I really like that it demonstrates how we can adapt this system to another engine in just a few minutes. Well, in a short time. We tested it yesterday and I really liked it. We even tried the DA90 engine, everyone's favorite with the Slavyanka winding, but we haven't figured out its encoder yet. I think we'll get it working a bit later. It does spin, but the torque is lousy. Well, shall we demonstrate how things are working for us? Well, I'll just chat a bit over there right away. There you go. This is the kind of software here for configuring ITD. It's very convenient and multifunctional. I was really surprised. Actually, Evgeny develops power electronics for machine tool servo drives, Lourdes A-stem. So that's why he managed to adapt all this pretty quickly.
So, shall we turn it on?
Yes, let's turn it on.
So, it's better not to stand in the plane again, just in case.
We're all about safety here.
Here we can demonstrate the RPMs. So, reverse gear, it spins in the opposite direction.
And its maximum is 6,000.
6,000, yes. Well, right now we haven't quite given it enough voltage. It's at about 4,600.
And by the way, how much does it consume at idle in total?
It's showing right now. Well, on average about 200 watts.
Yeah, 200 watts at idle for such a big engine. That's really not bad. There's almost no vibration at all. By the way, we need to be careful since we don't have galvanic isolation. There's a phase running around here somewhere. It could give you a shock.
Yeah. And by the way, when I suddenly released the gas pedal, the engine actually started generating a bit of energy while coasting. And since our capacitor's capacity is quite low and there's no ballast, like a resistor, or even better, a battery, it started charging it and the voltage on the DC bus began to rise. The system then went into protection mode because it detected that the voltage had jumped above 380 volts and for safety decided to shut everything down. So in real life, we use recuperation to the battery or with additional braking resistors, and then everything works fine.
It will work. But the main thing here is that we quickly figured out the resolver, so it didn't take much time, and it works right out of the box like this. Of course, without a test bench, we can't really load it, but in theory, it can deliver about 60 kilowatts. By the way, this Novito costs, well, I don't remember exactly, either 10 or 12,000 rubles, something like that. It's definitely a nice thing. Of course, you wouldn't buy these kinds of motors for production, but for DIY projects, it's really great. Just so you understand, a power module, like an Infineon one or some similar new class analog, costs about 1,000 rubles each. How many is that? 5, right? As I said. So as I understand it, you can even, this controller, well, this inverter works from 40 volts. Yes, 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 of course it has.
The efficiency is lower because after all there are IGBT switches here, the resistance is a bit higher, but if you want, yes, it works great. For example, with a battery from a 70 volt system, by the way, it's right here, we started it up and we were just testing the regeneration. Yes, and
everything worked fine, really, really, really well, no jerking at all. I wanted to say, I have something similar, one of these from our Chinese friends. Yes, we took it apart yesterday. Unfortunately, we didn't record it, but take my word for it, it's built on a similar principle, and the module is very similar to the Infineon one, just, well, it's Chinese, some kind of homemade version. And
it's about 1.5 times smaller in size.
This one here, how much is it in terms of power? Like 300 amps. Yeah, 300 amps, a 300 amp unit. At something like 336 volts. Well, something weird, basically. For this one, it costs about $40,000. So basically, there's not much to it, I'd say.
And by the way, I want to point out that these amps are kind of suspicious because this module here is 450 amps. I mean, it's a massive beast like this. And over there, it's just a tiny little module and it's almost 350 amps. Yeah, well, basically, these are Chinese amps, I think. So let's try connecting a different motor, see how well all this adapts, how quickly it all comes together.
And I don't remember what it's called. Oh, right, it's a starter generator with liquid cooling, also around 300 or 400 volts from some kind of Toyota. I like it because you can put it on some kind of electric bike directly. I mean, used ones are also available practically at scrap metal prices. You can
put a belt on it, yeah.
Yeah, for loaders, or you could rework it. It also has a resolver, as far as I understand. And a resolver is much better than Hall sensors, right? Yeah.
The resolver, first of all, inherently gives you an absolute value. And secondly, it possesses a high resolution. Because of this, at any given moment, even with a real physical motor, we can precisely know the rotor's position. And accordingly, we can accurately form the magnetic field exactly for the correct torque.
Yeah, I would have been blown up by the speech. Yes, that is it.
Yes, we tested it with a high current and he wanted to jump off the table.
Yeah.
No, I'm not interested in going this way. I need to go back. In general, it will start to somersault backwards.
Yeah. Yes, right now, because of the high current. Right now.
Yeah, because of the high, again, accelerated, suddenly let off the gas, and at high RPMs, again, it generated too much energy. Turned it off, cleared the error. Yeah, the generator, interestingly, would have turned out pretty good.
Turned out,
yeah, it's not bad.
The generator.
Right? Yeah. In fact, in some electric cars, there are two identical motors. One is put in the internal combustion engine, and the other is connected to the wheels. Yeah. By the way, something was done. The motor on this one, they just rewound it. I know people are afraid of high voltage, but for me, the more the better. If everything is properly insulated and connected, then it won't even be afraid of water. By the way, can you show how the resolver works? Yeah, I want to show how the resolver works. Listen, do we need some kind of temperature sensor for this? these wires at speed. Yeah, that's a temperature sensor. Right now, by the way, later in the controller, you should also plan to add a temperature sensor. And the motor already has one built in.
Built in?
Yeah, it's built in. It measures the module's temperature and you can connect. How do you connect to an NTC?
Or something like that, like a resistor on the train.
Yeah. There's an analog input there, and then it's up to you.
That's cool, yeah, a resolver.
Would work.
Actually, you can even get it in radians. Yeah, right away.
So right now we have two graphs. One is the sine component of the resolver, and the other is the cosine component. You started...
By the way, can you explain what a resolver is? Well, I
wanted to add that if anyone's interested, they can actually read about it on Wikipedia. Basically, it's a rotating transformer that ultimately produces two signals at its output, a sine and a cosine. And accordingly, when we rotate it, we get a sine wave on one output and a cosine wave on the other. And by using simple mathematical operations like arctangent, we can immediately determine the absolute angle, or more precisely, the absolute position of the motor's rotor at any point. And if we rotate it, as we're about to do now, we'll see it.
Well, that's because I'm turning it in jerks. I can't do it smoothly. So,
here, apparently, it's just from two phases at 90 degrees.
There it is. Yes, there it is. It works very precisely, very reliably, and...
Yes, the most important thing is that essentially it's just a piece of metal. The windings are potted inside. It's not a precision device because it's not some kind of servo drive where you need to catch the position with accuracy down to angular minutes or seconds. It's used for commutation. Accordingly, it's made to be reliable, and you can drop it, basically even hit it, and nothing will happen to it. But if you were to install, say, an optical encoder here, then you'd have to be much more careful.
Well, yes, let's start this one up. Yes!
Now I just need to quickly reconfigure it. This is our starter. We transfer the settings, save them. We set up the transmission. By the way, it probably has this starter generator, but at the time it had decent torque, so it could handle this kind of thing. Since it was running an internal combustion engine, yeah, I think it will have good torque, so here it's at the minimum. We turn on the voltage and we observe 37 volts, which is a little bit low. That's...
Just a second, I'll close the door.
Maybe it's because of that then.
With 3 motors, so if...
Yeah, that would be really sluggish.
Zhenya says, since it's all set up, if you have proper control, you can basically make one controller that somehow manages all the modules at the same time. You could, for example, make the inner wheel go slower and the outer one faster, specifically so it really turns sharply.
Oh, and like this, I think it'll be easy to see, right?
Here we go.
Alright, we have successfully turned on the fan.
Wow, it runs pretty quietly, doesn't it? Yeah.
I've noticed the car engines actually run really well, and in other setups too.
And which output is this even on?
And that's only 80 volts. I don't know if we use high voltage.
We could try it.
Give it a spin.
Yeah, well, it won't explode. Apparently, it can handle 300 volts.
Go ahead for now.
Yeah. Later, we should read the datasheet for it.
240 volts.
Yeah. How much in reverse, though?
5. 5,500. Well, and it's actually pretty sharp.
Yeah. Well, let's just say it's a starter generator, and, well, with a resolver, I kind of like how it works more than with Hall sensors.
Yeah. With Hall sensors, they work fine. The motors already get up to speed, so basically, the point is that Hall sensors are mainly used just to start the motor. And after that, it operates based on back EMF, but the back EMF system only works well on BLDC motors, as they're called, with clearly defined magnetic poles. But for the most part, automotive motors are still made using PMSM technology, meaning they have a specific winding, they provide a more consistent torque, everything's good, but with back EMF, it's more complicated to control them. That's why they use a resolver, and besides, a resolver is reliable, which is important for a car. By the way, I don't understand why Chinese motors, the low-power ones, use Hall sensors. Is there really that big of a price difference, or is it just harder to implement the interface? It's harder to implement the interface, plus it's not really necessary. For example, a BLDC motor for some kind of model aircraft or something like that, it practically never runs while stationary. That is, it's always spinning at high RPMs, and in that case, everything works fine.
Yeah, like when Nagoda tried it out, he attached it to a bike, and until you get it moving, at low speed it jerks around like it's paralyzed.
Even, by the way, those old servo drives which often have Hall sensors and an encoder, specifically an incremental encoder. The point is, with incremental encoders it can't start up because until it catches any mark, it can't orient itself. Yes, you have to do one the other way around. So it makes the first revolution using the Hall sensor, and after that, as long as you don't cut the power, it works off the encoder.
In short, a resolver is the best solution. Yes.
Yeah.
Well, all right.
It's cheap and reliable. By the way, just for fun, we could unscrew the cover and show what a resolver looks like. Yes?
Yeah, let's do it. Here's where the resolver is hidden. I've seen people, even on YouTube, rewinding them for some reason. I don't know.
You mean the motors, yes.
Yeah, they remove the resolver from the motor and install Hall sensors instead. I don't get it. I don't know why people are afraid of high voltage. To me, it's actually simpler. The wires are really thin. Here.
The resolver itself, if you look closer, you can actually see its magnetic poles there, by the way. So most likely this isn't exactly the classic resolver design, let's say, from Wikipedia. It's been optimized, modified, but that's how it is. So here you can clearly see the stator. Its core is also made up of stacked plates, and the rotor is also iron, and inside it there are windings hidden as well. By the way, the amplitude, the signal here is pretty big, isn't it? The amplitude is 0.5 volt. So that's normal. Yeah, that's normal. You don't need any millivolt or anything like that. It's not for
an inductor. Yeah, you don't need
to pull out any millivolts here.
So it's clearly a good signal.
Definitely, yeah, a good strong signal.
So we've quickly hooked up the ever popular, famous motors, the so-called Slavyanka motors. This is the DA90, I think it's called. I don't really remember. It's rated for either 3 or 5 kilowatts, I think. But we won't be able to start it up properly because it has its own specific encoder, and Evgeny just noticed it now. This is, well, the motor. Just got it yesterday, and I think we'll be able to set it up without any problems later. The encoder works. It's installed right here. Yeah. Well, for now, without position detection, we'll just show that it spins. Later, I'm really interested to work with you. We'll assemble load stands and push them to the limit, see what it can really do. We'll see what we can get out of it, what efficiency and so on. I don't think it's particularly bad or good. I figured it's not fundamentally different from other asynchronous motors. It'll have the same issues like low torque at low RPMs, but they're cheaper and there's nothing complicated inside. Well, let's demonstrate. Let's try to spin it up now. A bit.
Just a bit, yeah, in this direction.
Yeah.
By the way, this is an asynchronous motor, so right now it's basically going to operate in the mode of a Chinese frequency inverter.
Got it.
Okay, just turned it on.
So it does have some torque, right?
Yeah, there's some torque.
Again, I need to overload it, but its RPMs are low, right?
Low RPM, it's something like, well, I can't even precisely tell you the exact number right now, but it's also a multi-pole motor, which means it has multiple magnetic poles. So at this current moment, it's probably operating at approximately, around 870 revolutions per minute. It's essentially functioning like a 4-pole motor, I would guess, based on its characteristics and design.
Probably. We should check. There's a data sheet for it. And what voltage are you running it at right now?
Right now, 140. And this one, I don't remember, by the way, is there even a voltage rating for it? Yeah, like I said, there are no specs, nothing is known about it, so I just roughly picked the parameters by guesswork just to get it running and test it, that's all. Well, yeah, that's
not the right way. We'll set it up properly later.
So,
well, folks, now we've hooked up the motor, kind of like the ones used for skateboards.
It
looks like a model aircraft outrunner, just with Hall sensors. So we're showing that you can basically use any kind of thing as long as it has 3 phases and some kind of position sensors. You could even use, well, a simple DC motor, for example, and it would work too. By the way, this could actually be really useful for a turbine starter, since it can smoothly spin it up with current limiting. Otherwise, you have to deal with 1,400 amps.
You have to use a contactor.
Yeah, and the contactor, we used to clamp it down so hard, this would be a useful thing. So let's demonstrate how it works at 36 volts. Next. It's crooked and misaligned here. It runs pretty smoothly, just a little bit. Yeah. The bearings are rattling. It's got some play, yeah? Yeah.
There you go.
By the way, how much does it draw at idle? I'm curious if it's worth running it.
It's tricky. It doesn't really measure the power correctly on this motor, so
that is it.
You don't need to record that, it shows negative power. It has very low inductance in the windings, so for this particular motor I had to make some compensation. And this compensation is applied only after, let's say, the initial voltage values are accurately taken and recorded, so the resulting readings are consequently a bit inaccurate and might require further adjustment. That's it. Well, gentlemen, I truly think this important inverter project
is in the lead right now. We'll see. I'll be reviewing the other projects in detail, but I think we'll also have a second place because I really like everything about this. And most importantly, it's a finished, well, you could say it's already a prototype and it's not too far from production, though there are some things to work out, etc. As you can see, the inverter turned out to be very versatile, and I really like that. We'll see, once we set up the test bench and everything is running under load under serious conditions, about 60 kilowatts, then well, let's say it'll be proper. But that will depend more on the power module. If it's cooled properly, everything should be fine. Maybe we'll need to tweak the control system a bit. But for that, we'll need to actually set up 60 kilowatts. There's no way you'll find enough Variacs for that. You need something around 100 kVA. And we'll have to assemble a battery, at least with a small capacity, but capable of decent current, and well, a load test bench. So I really liked it, and I think everything will turn out great. As they say, they can do it when they want to. So, what I want to say regarding the contest results is that we're having some communication issues here. Everyone is sick, and Ivan got sick too. Since he's also part of our judging panel, we can't make all the decisions without him. I hope he'll recover within a week, at least within a week. So we remember our responsibilities, so to speak, and we're working on finalizing the results. Please wait just a week, at most 10 days, and we'll announce the winners. In short, we received a lot of applications. Many of them weren't really noteworthy, but there are some truly excellent projects among them. I'll post all the draft projects a bit later on the website dp.labs.ru, so you'll be able to check them out. All the best, subscribe to the channel, give us a like, and goodbye.